Welcome to this project on norms and eigendecomposition, linear algebra with Numpy, presented by Eduonix. Today we are going to be building a notebook that will hopefully enforce some of our understanding of eigenvalues and eigenvectors, what they look like, how do we find them, as well as the process of normalization. We're going to cover norms as well. As usual, I'm going to build this project in a Jupyter notebook, and I'm going to do it right there along with you, step by step, line by line. So follow along, and we can do this together. All right, to start, I'm going to open up my command prompt. Again, I'm in Windows 10, so if you're working on a Windows machine, you'll be able to follow along exactly. If you're working on a Mac or Linux machine, then there might be some slight modifications, at least in this original terminal. All right, so I'm going to be over in my tutorial folder, and to start a Jupyter Lab notebook here, you just type Jupyter Lab. As always, click Enter, and that will get that going. And that should be all configured from past projects that we have done here together. If you don't have it installed, go ahead and install Jupyter Lab right now. All right, so I'm just doing a default Python notebook here. So I can click on the Python default. And Jupyter Lab is going to show you a directory over here. If it doesn't, click Control B. I have the matrices project that we did together not too long ago, and we're going to start this one here today. So this will be EigenDecomposition. All right. So let's go ahead and get started. First things first, as always, let's make sure that we are using the same packages. So import sys, this will tell us our Python version. I'm using Python 2.7. I'm going to import NumPy. I'll do it as NP. And let's go ahead and print out the version numbers here so that we can ensure we have similar setups. Print NumPy .format NP version. All right, Shift Enter will run that. And it'll think for a second. So again, I'm using Python 2.7. It'll show that here in a second. There we go. Python 2.7 on a 64-bit Windows machine. And then NumPy 1.141. All right, so there's that. One other thing that we're going to need is from NumPy, we need to import their Linear Algebra package. So just linalg. We'll import that. This will give us some helpful linear algebra functions that we're going to be using today, such as norms. And actually, that's what we're going to go into first. So let's start by defining an array. So define an array, and we can just call it matrix A or array A. This isn't going to be a matrix yet. And let's just do range 9. So this is 0 to 8. And I'll just do -3 so we can get some numbers in there. If we print off A, you see now we have the linear vector here going from -3 all the way to 5, integer steps. Let's reshape this into a matrix here. So we can simply do A.reshape, and we'll make it a 3x3 matrix. So if we print out B now, we see we got the corresponding 3x3 matrix to this vector. And the reason I've done it this way is so that we can compare the norms for a vector A to a similar matrix B. All right, so let's start. Using norms in NumPy with their linear algebra package is really straightforward. We're going to start with the Euclidean L2 norm, and this is actually going to be the default, so we don't even have to pass any parameters to this other than the matrix. Let's print out both of these, norm, and we'll do it for B as well. And you see the L2 norm is actually going to be exactly the same. We talked about the Frobenius norm, which is simply the L2 norm for a matrix C, so it's going to do that as well. And so we get the same answer for the matrix and vector in this case. And that is indeed the Frobenius norm. So if we show this, Frobenius norm is the L2 norm for a matrix, and we can see that by actually asking this linear algebra package to do a Frobenius norm, which is just denoted with this fro here. We got a nice fro for Frobenius. And if we run that, we see indeed we get the exact same answer. And that's because they're running the same norms. All right, some other things that we can do with this. We can do the max norm, and that's when p is equal to infinity. And we do that by passing it the p value here, which is just going to be np dot infinity. B np dot infinity. And so you see we actually get some different answers here. In the case of the vector, the max norm is going to simplify down into the largest value, which is 5. However, that's not exactly the case for the matrix. So some differences there. Let's look at the vectors a little bit. And vector normalization. You could also, just to note before we move on, you could use any number here. So example, if we wanted to do the L1 norm, you could find that as well. So it's really easy to change around those parameters and get the L1, L2, or Frobenius, whatever you might need, max norm. So finding the norms in Numpy, really straightforward and easy and quick to calculate. And you need those because of vector normalization. So this is normalization to produce a unit vector. And oftentimes in machine learning, we want to normalize our data between 0 and 1. So this is a very helpful operation here. Again, let's take the norm of A, and this is a 2. The 2 is a default, so you don't need the 2 here. This is just the L2 norm. And then remember, our process of normalization involves dividing the matrix by the magnitude. That is normalization. The magnitude here is going to be the L2 norm. So if we have the unit vector of A here, is just going to be A divided by now the magnitude, which we just calculated. So let's go ahead and print out that A unit. And here we go. This is indeed going to be the unit vector for corresponding to A. And so we can check that by saying the magnitude of a unit vector is equal to 1. Remember, that is the defining characteristic of a unit vector. So we can actually calculate that just to double check, and we'll do the L2 norm of a unit. And indeed, we get back out 1 to show that, yes, this is a unit vector. It is normalized between 0 and 1. So there we go. That's how you normalize a vector. Again, normalization is an essential pre-processing step in most machine learning algorithms. So make sure you normalize your data. Even in like deep learning, you want to have even classes, normalized classes and frequencies. So normalization, since this machine learning is a statistical process, normalization is very, very important. All right, and that brings us down here to eigendecomposition. So I'm going to copy in some information here from the side. We change this to a markdown cell. We're going to have some LaTeX formatting here. And there we go. To actually display these formulas for us. All right. So eigenvalues and eigenvectors. Hopefully you listened to the lecture first. We just talked about them. But they're easy to find using Numpy and Python. Remember the eigenvector of a square matrix A is a non-zero vector V such that multiplication by A alters only the scale of V. And this is the formula for that here, showing V multiplication by A is only going to scale V by this eigenvalue lambda here. And you see that here. So let's go ahead and do that. And that's actually what we're going to be looking at today. We're going to be looking at the scaling of these eigenvectors and eigenvalues. We're going to do a cool 3-dimensional plot to show that. All right, so find the eigenvalues and eigenvectors for a simple square matrix. And when I say simple, I mean simple. We're going to keep this very simple. A range 1 to 4. And this is how simple we're going to keep it. 1, 2, 3 on the diagonal, zeros everywhere else. Recall back to our our lecture on special matrices and vectors. Here we see we have a diagonal matrix. We have values on the main diagonal running top left to bottom right, zeros everywhere else. All right, and here's how easy it is in Python. Eigenvalues, eigenvectors equals np.linalg.eig of A. And then when you run that, you have the eigenvalues and eigenvectors. So that is really quick. So let's see these. So it returns the eigenvalues, and we can print these out. So eigenvalues, we have 1, 2, and 3. And then it also returns the eigenvectors. And here we go with the eigenvectors. And remember, the eigenvectors are stored in a matrix with each column corresponding to an eigenvector. So we have 3 eigenvectors here. We have 1, 0, 0, 0, 1, 0, and 0, 0, 1. So 3 eigenvectors. Each column is an eigenvector. And we have eigenvalues that correspond to those. So the eigenvalue, and we'll call this W, W of I, corresponds to the eigenvector V, and here we have a colon just to show that every row, so we'll take a column, and then the column I is the corresponding eigenvector. So let's print those out just to show eigenvalue. Let's say dot format. Eigenvalues, we'll just take the first one, or the second actually in the array. It's going to correspond to the eigenvector here, dot format. Eigenvectors, we'll take the entire column, use a colon, and then 1. So we get that. We see the eigenvalue 2 here corresponds to the eigenvector 0, 1, 0. And that's exactly what we would indeed expect. Okay, so we found those, but how do we know if they're right? Well, we can actually easily check this using the EigenDecomposition formula. And that's what we're going to do. Oh, I apologize about that. Let me see if I can get this here. There we go, that's better. Here we have the EigenDecomposition formula. So we're actually able to check this, and what we're going to do is simply find these different matrices. We have V, that is all our eigenvectors. The diagonal of lambda we can make, and then this is going to be the inverse of our eigenvectors, and we should get out our original matrix. So let's check that. We'll just have actually let's add a comment here. Verify EigenDecomposition. So an intermediate matrix here is going to be np.mapmul. This is matrix multiplication. What I'm going to do is I'm going to multiply these second 2 matrices first, and then we'll multiply it by the first one after that. So we'll do np.diagonal eigenvalues. And maybe if we add in, we can show what these are doing. np.diagonal eigenvalues. This is going to return an array with the eigenvalues on the diagonal. In this case, it's actually the original, and that's just coincidental. All right, so we have that. Diagonals, eigenvalues, and then np.linearalgebra.inverse of the eigenvectors. And let's take a look at that one actually as well. Linear algebra.inverse eigenvectors. It's going to return this matrix, which is actually the exact same matrix, because multiplication is going to give you this right back out, which is going to give you the identity matrix here. Since our eigenvectors are an identity matrix, actually, multiplication by itself, 1 times 1, is still just going to be 1. Again, just coincidental, because we're using such a simple matrix here. All right, so here's our intermediate, and then our output is going to be equal to another matrix multiplication. the eigenvectors times that intermediate matrix we just made. We'll say as type np.int will return integers, and let's print this output. And indeed, we get back out our original matrix. All right, so that's pretty cool. We were able to verify using the formula for eigendecomposition that Numpy actually correctly calculated the eigenvalues and eigenvectors for us. So we were able to verify that using that equation, going through eigendecomposition in Python and Numpy. So eigenvectors and eigenvalues can often seem difficult conceptually, and it's really helpful to visualize the eigenvectors and their multiplication with the original matrix A. So using matplotlib, we are going to try to accomplish that ourselves. So let's go ahead and do that now. What we're going to do is we're going to import necessary matplotlib libraries, and we have a 3 by 3 vector matrix here. So we're actually going to do this in 3D. So it's going to look very cool at the end. So import pyplot as plt as always. One other thing we're going to need is from mpl toolkits.mplot3d, which you should have installed if you have matplotlib, axis 3d. And this is going to enable us to use 3 dimensions here. We also need to import matplotlib, or we actually don't need the color map. We need to do a magic command here, magic Python command, inline, so that we'll display these graphs right here in our Jupyter notebook. All right, so go ahead and import those. And then we are going to plot them. So let's just start plot the eigenvectors. We're going to plot them in a matplotlib plot, 3 dimensions. The origin we need to define before we start, 0, 0, 0. That makes sense. And this is going to be x, y, and z. So 0 on all 3 fronts. All right, let's make a pyplot figure. So we'll say figure equals plt.figure. And just for formatting, let's add a figure size here equals 18 by 10. That'll make it nice looking for us. Let's add an axis here is actually what we're going to add next. So we'll do these in subplots. So we'll say axis equals figure.add subplot, so we can do a side-by-side comparison of before multiplication and after multiplication. And we need to add a projection here. So projection is going to be equal to 3D. So this is the first of 2 subplots, 1 row, 2 columns. And what we're going to use is we're going to use a quiver plot. So axis1.quiver, and we're going to have to add the origin here. We have 3 eigenvectors, so we're actually going to have to add it 3 times. And what this is going to be doing is this is an array of the x points for the eigenvectors, a 3 length vector for the y's, and the same for the z's. And you'll see why that's important in a second, because when we add on here is going to be the eigenvectors and the x for all the eigenvectors. So instead of taking the column here, we're going to take the row. And then we're going to take the y for all the eigenvectors. And we'll take the z for all the eigenvectors as well. Let's make this a little nicer. We'll add a color here, just K. Make it black. It'll make it nice and visible. All right, so we've added on our eigenvectors. Let's format this a little bit. So we'll set x limit -3 to 3. Axis 1 dot set y limit -3 to 3. There we go. And since we're 3-dimensional, we actually have to set z limit as well. And we'll do a -3 to 3 as well. Give us a nice square. Cube in this case, actually. Okay, let's add some labels. X label, we'll simply call x-axis so we can keep track of these. axis1 dot set y label y axis, axis1 dot set z label z axis. All right, here we go. Just making our way through this kind of unexciting formatting here. But that's all right because it's going to give us a really exciting graph in the end. We'll set an angle to be viewing this three-dimensional plot so we're not viewing it straight on. And let's finally give it a title. Say before multiplication. All right. So there we go. These should be our original eigenvectors. Let's go ahead and plot this. So plt.show is going to bring up this plot. Right now it's only going to have one plot since we haven't added the second subplot. Let's go ahead and run this for now and see what we're able to get. So here we go. Here's our nicely formatted vectors. We have three eigenvectors corresponding to the ones that we found up above. We have 1, 0, 0 is going to correspond to 1 on the x-axis. It's actually going to be this one. 0, 1, 0 is going to be the y-axis. That's what we have here. And 0, 0, 1 is going to be on the z-axis. That's what you have here. So each of these 1, 0, 0 corresponds to the x-axis. 0, 1, 0, that's the y-axis. And then 0, 0, 1, z-axis. And that's exactly what you're seeing. 3 length 1 vectors on the corresponding 3 axes. All right, so there's that. Let's go ahead and multiply this by the original matrix so we can see its effect. So we'll say new eigs, we'll just say called new vectors or something like that. NP matrix multiplication A eigenvectors. So multiplying by the original matrix, add some spaces here. And axis 2, we'll say we gotta define that plt.subplot 1, 2, 2. So the second subplot now, projection equals 3D. All right, let's add these on. To save time, I am going to copy some of the information from up above. In fact, I'm going to copy all of the information, and then we can go through and just change what we need to. So axis 2, the origin should still be the same. Instead of the eigenvectors, now what we want is we want the new eigenvectors. So we'll change these. Plotting them the same way using the x, y, and z points. New eigenvectors. All right. And one other thing I want to do is I want to add the eigenvalues to the plot so that we can see these as well. So axis 2, I want to plot. And to plot these, we're just going to multiply the eigenvalues. So eigenvalue 0 times its corresponding eigenvectors. That way it displays on the correct axis. So we'll have that. And let's go ahead and just highlight this and Control Z, copy this 3 times. Trying to save some time here so that you don't have to write all of this out by hand. Go back here, we can change these to 1s so that we have our second one here. And then finally our third one, index 2. All right, so there's our eigenvalues. Good to go there. Changing these to a 2, we want to format the second axis. The labels are going to be the same. Title, we're going to want to change that. This is no longer before multiplication. It is indeed after multiplication. So there we go. One other thing, I want to come back up here and I want to add a super title. So I want to do figure.subtitle over all of this. So effects of eigenvalues and eigenvectors, just so we know what we're looking at. All right, so we should be good to go. We have our second subplot here. It's a three-dimensional subplot denoted by the projection 3D here, multiplying the eigenvectors by the original matrix. What this should do is this should scale and shrink each one of these vectors by the corresponding eigenvalue according to the equation that we had up here. So we should see shrinking or scaling. We shouldn't see any distortion in the angle of the vectors. So let's take a look. So as this thinks for a second, here we go. And indeed, we're able to produce a very nice subplot on the right here, showing these new vectors and how they've been scaled. And this actually makes perfect sense. So our first eigenvector, we had 1, 0, 0. That's a 1 on the x-axis, a 0 on the y, and a 0 on the z. The corresponding eigenvalue to that vector was 1. And so you see that it doesn't get scaled at all. And we can see that up above here. The corresponding eigenvalue is 1 corresponding to the 1, 0, 0. The 0, 1, 0, which is on the y-axis, should have a 2, and that's exactly what it has. So here we have 0, 1, 0 going on the y-axis. It was scaled by a 2, so it's now a length 2, and it is going all the way out to that eigenvalue. On the z-axis, similarly, we had an eigenvalue of 3, so that eigenvector gets scaled 3 times, and we now have a length 3 vector coming up here on the z-axis. So very cool. We're able to show that, yes, the eigenvectors are only scaled by the corresponding eigenvalue when they're multiplied by the original matrix. So this visualization really helps me kind of conceptualize what's going on with eigenvalues and eigenvectors and this representation of the matrix that we generate when we find the eigenvectors and eigenvalues. All right, so that's actually going to bring us to the end of this project. I hope this visualization helps you kind of conceptualize the idea behind eigenvectors and eigenvalues. As we've seen, it's really easy to find them in Python. However, it's more difficult to think of them conceptually. So when these come up in a machine learning paper that you're reading, now hopefully you can kind of understand what is going on. Also, we talked about normalization. This might be the most useful piece of information that you're going to take away from this project, how to normalize a vector. Also, there's many just normalization functions out there. Scikit-learn, if you're using scikit-learn to do machine learning, has a preprocess.normalize function, which will do this all wrapped up into one for you, but it's not a long process if you have to do it manually. Remember, normalizing your inputs, very important for machine learning. And we looked at some of the other norms as well that might come up. All right, I hope this gave you some functional capabilities to do some of the math that we've been talking about, as well as helping kind of reinforce some of the theory behind it as well. Thank you very much for participating.